We're now looking at graphs for quantitative variables. First type of graph we're looking at is a dot plot. Dot plot, real basically, you just create a scale. In this case, it looks like my smallest number is 0, my largest number is 6, so I'm going to list everything from 0 to 6. 0, 1, 2, 3, 4, 5, and 6. Now I'm just very simply going to put a dot every time a number appears. So here's a 2, I'm going to put a dot at 2. I get another 2, I put a dot directly above it. So as you can see, as I was doing the process, all I did was put the same mark above each one. Goal is for us to be able to basically make a histogram out of this, to compare things. So essentially this turns into a bar of about that height, that height, and so on. But a dot plot builds us towards where we're going to be doing histograms eventually in the next section. What I can do is I can look at the shape of this and I can describe it. So in this case, the data is piled up on the left. It has a longer right tail. That's why it's called right skewed. So I would say that this is a right skewed shape. When I'm asked if there's any outliers, this 6 stands out to me. I have a blank between it. Really, most of the data is over here. This does look like it would be an outlier. So 6 is an outlier. There's different formal definitions for an outlier. There's times when the book says an outlier is anything that's more than 2 standard deviations away from the mean. There's times where when we're using box plots, they define an outlier as being more than 1.5 interquartile ranges from the 3rd quartile. There's weird, messy ways to say this mathematically counts as an outlier in different situations. In this part of the course, what we're more trying to say is there some data point that's far away from the rest of them? We're not using a mathematical definition. We're not testing these points to see whether they're outliers. It's more by inspection, just by looking at the graph saying, well, this looks like it's out of place. It's far away from everything else. Part B asks me what proportion of the measurements are greater than 3. So in order to figure out what proportion, we're going to need both a numerator and denominator to the fraction. The denominator of the fraction is going to be how many it's out of. So there we want to count what's the total number of dots in our dot plot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So my denominator is going to be 17. Of those, which ones are greater than 3? Well, these are equal to 3, so they don't count. 4 is greater than 3, it counts. 6 is greater than 3, it counts. So 2 of the 17 are greater than 3. Usually you can just put it in as a fraction, 2 out of 17, and it would accept that as a proportion. If you did want to do it as a decimal, you could just put in 2 divided by 17, and it would give me 0.1176, which I'm going to call 0.118. Usually when they want you to do a decimal, they'll tell you how many digits to round to. I think it's probably better for these proportion questions if you leave them as fractions. Question 2 says, consider the following data set. Here we have 20 different numbers that are 2 digits. We're asked to construct a stem and leaf. So what I'm going to do is have my stems listed here as the whole numbers that are before the decimal point, have my leaves listed here as the numbers after the decimal point. When I look at my array of numbers, the smallest thing that I see is 2.1. The largest that I see is 5.7. So I'm going to go with my stems starting at 2, 3, 4, 5. And then I'm going to be putting the leaves next to it. I want to make sure the leaves are in ascending order, so I'm looking for the smallest first. Here's 2.1. I'm going to put a 1 next to this 2. Now I see that there's a 2.2 here and a 2.2 here. So I'm going to put 2, 2. Here I have 2.7. I think that's the only 2 remaining. So I'll put a 7 here. Next one for 3. The smallest that I see is 3.0. So I'm going to put a 0, stand for 3.0. Then I see this 3.1. After that, I see 3.3 listed 1, 2, 3 times. So I'm going to put 1, 2, 3, 3.3s. Next thing I see is a 3.5. Then a 3.6. Then a 3.8. And that's the end of the 3s. For the 4s, I start here with 4.2. Then I've got 4.4. Here I've got 4.9 and 4.8, so I put in 8 first and then 9. For the 5s, we have 0, 5, 5, and 7. So I put in 0, 5, 5, 7. 0, 5, 5, 7. In general, when I'm trying to do this many points at once, I like to double check before I submit anything, count that I have, yes, the right number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So now that I've got the correct stem and leaf, the one extra thing I want to add is a key. So this key is going to say 2 line 1 equals 2.1. Basically, I just want to make sure that everybody knows that stem and leaves aren't tens digits, ones digits. They're ones digits, tenths digits, or something after the decimal is what the leaves really represent. When I'm asked to describe the shape, what I'm really trying to do is turn it on its side and see what it would look like. So if I did that, I would see that really there's this one higher bar, then even bars on either side of it. Normally we would call that a symmetric distribution. I think this one's a little tricky. I genuinely just randomly came up with numbers. I could see how you might say uniform because they're all the same except for one that you might say was just kind of an aberration. I think maybe you could say that it's built up on the left and therefore would be skewed right. You could definitely make a case for some of the other ones, but to me, it looks mostly like a symmetric distribution where it's highest in the middle and lower on the outsides. Do I see any outliers? In this case, no. Everything's grouped up pretty close together, so I'm going to say no to the outlier question.